Hi, my name is Kristen. Welcome to this journey through digital product design and 3D printing. Today, we are going to study the chapter, which is Introduction to Simulation, CAE. In this chapter, we'll explore how engineers use simulation tools to predict the behavior of physical products under various conditions. We'll understand concepts like stress analysis, thermal effects, motion, and even fluid flow through basic CFD. Let's dive in and see how computer-aided engineering helps us design smarter and safer products. So, what is stress analysis? Stress analysis helps engineers understand how forces affect a material or structure. When an external load is applied, stress builds up inside the part. This can cause deformation or even failure. With CAE tools, we can simulate how a product will behave without physically building it. This saves time and resources in prototyping. It's essential in automotive, aerospace, and even consumer product industries. 3. Types of stress. There are different types of stress: tensile, compressive, and shear. CAE simulations show where each of these occurs in a design. The areas with maximum stress help us identify weak points. Color maps or contour plots in simulation results highlight these stress concentrations. Recognizing stress zones is critical for redesigning or reinforcing parts. 4. Understanding load conditions. Load conditions define how forces are applied to a part during simulation. These could be static, dynamic, or even impact loads. It's important to apply realistic boundary conditions, like fixed supports, point loads, or distributed pressures. If the loads are inaccurate, the simulation results won't reflect real-world behavior. Engineers often consult design specs or field data to define correct loads. 5. Real-world examples of loads. Think of a bridge. It experiences vehicle loads, wind loads, and its own weight. In a CAE simulation, we must replicate these using proper load conditions. Similarly, a bracket holding a motor may undergo vibration and twisting forces. Each load affects stress and deformation differently. The better we define these, the better our simulation outcome. 6. What is meshing? Meshing is the process of dividing a 3D model into small elements or cells. This allows the simulation software to solve equations on each element. A finer mesh gives more accurate results, but takes more computation time. A coarser mesh runs faster, but may miss critical details. The balance between speed and accuracy is a key skill in CAE. 7. Mesh quality matters. Good mesh quality ensures reliable simulation. Bad mesh with skewed or distorted elements can cause wrong results or errors. Some areas like holes or fillets may need finer meshing due to high stress concentration. Automatic meshing tools help, but sometimes manual refinement is needed. Mesh independence testing ensures that further refinement doesn't change the outcome much. 8. Understanding factor of safety. Factor of safety, FOS, tells us how much stronger a design is compared to the expected load. For example, if a part can take 1000 N, but is expected to carry only 500 N, the FOS is 2. Engineers design products with FOS to account for uncertainties, like material flaws or unexpected loads. In simulations, we often calculate FOS based on maximum stress. Higher FOS means safer design, but may increase cost or weight. 9. Choosing the right FOS. Different industries have different safety standards. Aircraft parts may require a high FOS due to passenger safety. Consumer electronics may use a lower FOS for cost reasons. Simulation tools in Fusion 360 or SolidWorks can calculate FOS maps. These highlight which areas are at risk of failure, guiding design improvements. 10. Introduction to thermal simulation. Thermal simulations analyze how heat moves through a part. This is important for engines, electronics, or even 3D printers. Heat can cause expansion, weakening, or thermal stress in materials. CAE tools can simulate conduction, convection, and radiation. With this data, we can improve cooling designs and material selection. 11. Applying thermal loads. In thermal simulations, we define heat sources, like a chip generating 50 W, and boundary conditions, like air cooling. Software then calculates temperature distribution and thermal stress. For example, simulating a heat sink's performance can prevent overheating. Understanding thermal profiles also helps us choose between materials like aluminum or copper. It's essential in product safety and reliability. 12. Basics of motion simulation. Motion simulation predicts how parts move under forces. It's useful for gears, linkages, or robotic arms. We simulate inputs like motors or gravity and observe resulting motion. This helps detect collisions or jamming early in the design phase. It also helps optimize motion paths and joint design. 13. Kinematics and dynamics. Motion simulation can be kinematic, motion without force, or dynamic, motion with force. Dynamic analysis includes forces, acceleration, and inertia. For example, simulating a car suspension helps see how it behaves on rough terrain. This data helps engineers fine-tune springs and dampers. Motion studies save time in physical prototyping. 14. What is CFD? CFD stands for Computational Fluid Dynamics. It's used to simulate fluid flow, pressure, and heat transfer. CFD helps design cooling systems, aerodynamic parts, or plumbing systems. We define fluid properties, inlets, outlets, and boundary conditions. Then the software calculates how the fluid behaves in and around our part. 15. Applications of CFD in design. CFD can be used to optimize fan housings, turbine blades, or HVAC systems. For example, engineers use it to reduce drag on car bodies. It also helps improve fuel efficiency by simulating airflow in combustion chambers. Though complex, basic CFD tools in Fusion 360 give mechanical students a starting point. It's an exciting intersection of thermodynamics, fluid mechanics, and software. 16. Setting up the case study. Let's explore a simple case study using Fusion 360. Imagine a bike pedal bracket being tested for stress and safety. We import the 3D model and assign aluminum as the material. Next, we fix one end and apply a force where the pedal meets the bracket. Then, we generate a mesh and run the simulation. 17. Analyzing the results. The results show maximum stress around the mounting holes. The factor of safety map highlights potential failure zones. With this info, we can redesign the bracket with fillets or thicker regions. Simulation saves multiple iterations of physical testing. Fusion 360 provides visuals and data that are easy to interpret, even for beginners. 18. Adding thermal and motion conditions. Next, we simulate how the bracket heats up during use. Heat from friction is added, and thermal expansion is observed. We also simulate the pedal's motion using rotary joints and input torque. Combining stress, thermal, and motion helps us understand the part fully. This multi-physics approach is the future of engineering design. 19. Recap and takeaways. Today, we learned how CAE tools help engineers simulate real-world behavior digitally. From stress analysis to CFD, simulations offer deep insights. Key steps include defining geometry, loads, materials, and meshing. We also saw how Fusion 360 allows us to test and improve designs efficiently. Mastery of CAE can make you a powerful design engineer.